We're going to use the Riemann sum with 6 subintervals or 6 rectangles to estimate the area under the function f of x equals x squared from 0 to 3. And we're using the left endpoints for this first graph, and then next we're going to use the right endpoints for the example below. So the first thing I want to do is draw you a picture of what's happening here. This is the graph of f of x equals x squared from 0 to, we're going to go as high as 3. I'm going to split this into 6 subintervals. There's my 6 subintervals. I am going to identify these x coordinates. We've got 0.5, 1, 1.5, 2, 2.5, and 3. We're asked to use the left endpoints to start us out to come up with the left corner of our rectangles. So the left endpoint of the first rectangle is going to be at 0. And the next rectangle will have a left endpoint at 0.5. So far this is what's happening. The first rectangle goes nowhere, okay? Because the left endpoint decides the height. And if I plug 0 into my function right here, f of x equals x squared, my output value is 0, right? So that tells you the height of the first rectangle is 0. But the next rectangle now has a height of whatever f of 0.5 is. F of 0.5, 0.5 squared, 0.25. And then the next rectangle is going to have a height based on what f of 1 is. And so f of 1 gives you 1. So the height of that next rectangle is 1. And so on and so forth. So I'm looking at all of these heights. The heights are determined by the left endpoint as was specified in your problem. And I'm plugging in each of those left endpoints into my function to figure out the output value, which tells you the height of that rectangle. Next, it says to estimate the area under this function from 0 to 3 using the left endpoints. And so the Riemann sum is found by taking the limit as n goes to infinity of f of x1 plus dot 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 plus f of xn times delta x. Right? That's the general version of the Riemann sum. Here we're asked to go with 6 subintervals, and so we are going to use our information, f of 0 plus f of 0.5 plus f of 1, and so on and so forth, all the way down to f of 2.5. And each of these will get multiplied by delta x. So delta x, remember from above, is found by taking the distance from the left endpoint to the right endpoint. So we subtract 3 minus 0, and we divide by 6 to tell us that we would get a width equal to 0.5. So you just plug in each of those f values. I'll go ahead and write it out for you this time. 0 plus 0.25 plus 1 plus 2.25 plus 4 plus 6.20. You can see it's a pretty consuming process here. It's not complicated. It just takes a little while, a lot of places, to make a mistake. So just take your time on this so that you don't make any arithmetic mistakes. So that would be your approximate answer for the area under the curve from 0 to 3 of the function f of x squared, using left endpoints to construct your rectangles. Do it again, but this time we're going to be using the right endpoints to determine the width of our rectangles. So I'm splitting this into 6 subintervals once again. It goes from 0 to 3. The distance is 0.5. So make a note that delta x is still 0.5. And the right endpoints is what I want to put in my table. And I want to compute f of those values, and that's going to tell me the height of each rectangle. So the first rectangle has a height of f of 0.5. And the second rectangle has a height of f of 1. And so these are now the rectangles whose areas I'm going to be calculating and adding together. And can you kind of see that this answer is going to be an overestimate of what it should have been because I've got extra area that I shouldn't have. And then the answer above was an underestimate because of all of those gaps that I didn't have. Look at these gaps. There's gaps here. There's a gap here, some space here. And so I am not accounting for that. But in this graph that I'm constructing right now, I've got an overestimate. I've got extra pieces of area that I'm not supposed to have. And so that's going to give me an overestimate of the true area. But in any case, it's an estimate. We'll take it for what it's worth. And I'm not going to write out all the work this time. I'll just tell you what you should get. The total area that you accumulate is going to be 11.375 square units. All right, so that one is definitely bigger than what we got above. The real answer is going to be somewhere in between. Okay, but anyway, this is the Riemann sum. It's used as an approximation of the area underneath a curve between two endpoints A to B. This leads us to the definite integral. We've talked about the indefinite integral in the first two sections of this chapter. The definite integral is going to include the integration bounds, the bounds of integration from A to B. Right? A is the left endpoint, B is the right endpoint. We're taking the integral of f of x with respect to x. This is the idea of the Riemann sum that we learned about back here. Okay. Now it doesn't make any sense theoretically, practically. It doesn't make practical sense to actually construct more and more and more subintervals and accumulate all of this area. So we need a shorthand way of doing that, and that is where the integral comes into play. This integral is going to give you the area beneath the curve from A to B. And so this definite integral that we're going to get is going to give us an answer that is a number. We will not have plus c. We will no plus c in these answers. However, when we learned about the indefinite integral in the previous sections, we did have a plus c, which is why we considered our answer to be a family of functions, each involving a different particular constant. All right, but for the definite integral, we just get one answer, and that's it. There's no if or but. There's no gray area. It is what it is. So there's your picture of what the area would look like under a curve between A and B. That is what we are counting and counting up. And we're not going to do it with rectangles this time. That gives us the approximation. We're actually going to use techniques of integration. For this first example, you'll notice that it specifies that f of x is greater than or equal to 0. Okay, so focus on that for now, and then we'll mix it up in a little bit. But if your function is strictly above the x-axis, that's what it means to be greater than or equal to 0 on or above the x-axis, all right, so it doesn't go below. From A to B, the region R, which is the area between the curve and the x-axis from A to B, it has area A given by the definite integral from A to B of f of x dx. Okay, next comes the fundamental theorem of calculus. I'm going to abbreviate that by FTC for short. The fundamental theorem of calculus says if the function f is continuous over an interval a to b, then the integral of f of x from a to b equals, there's your f of x, big F of x that we learned about in the last section, from a to b. So it's from the bottom number to the top number is equal to f of the top number minus f of the bottom number. And that is how you compute your definite integral, which gives you the amount of area from A to B. So for the first case, as I mentioned up above, your function is completely positive, so it stays on or above the x-axis. And when you integrate from A to B, when this function is continuous from A to B, then that gives you the exact area between the function and the x-axis. That is the exact area. How much area is there? The exact area, okay? The second case is where some of the graph is above the x-axis and maybe some of it goes below and it wiggles around up and down like that. And in that case number 2, Your function is still continuous, which needs to be true in general. But now f is either positive or maybe sometimes negative or sometimes a combination of both. Then the definite integral gives you the exact change in area over the interval from a to b, all right? So how much did it change by from here to the end? How much did the area go up? How much did it go down? I like to think of this in terms of like either money or temperature or something like that, where you win some, you lose some, right? So from 0 to 2, when we start out, the area is above the x-axis, so we consider that to be a positive quantity. We're gaining money, we're gaining degrees. It's getting warmer outside. The temperature is going up, but then from 2 to 4. It goes below the x-axis. Now we're either losing money or the temperature is going down. And so this would be considered a negative amount. It's going down by whatever 9 units represents in that case. All right, and then it's above. So now we're gaining momentum. We're earning money, or we are the temperature is getting warmer. But then from 6 to 8, now we're down below again. So we are spending money, the temperature is getting colder, it's going down. And then after that, from 8 to 10, it's positive again. So basically you need to understand that anytime the area is above the x-axis, it's a positive amount. And anytime the quantity of area is under the x-axis, it would be a subtraction, a decreasing of that amount. And so in this particular graph's example, from 0 to 10, the entire integral from 0 to 10 of the area would not be 15 plus 9 plus 6 plus 5 plus 3. You have to consider sometimes it's positive, sometimes it's a negative change. And so that means you have to take 15 minus 9 plus 6 minus 5 plus 3 altogether. The difference from the beginning to the end is you gained 10 because it's positive. So overall, either I have an extra $10 or it's an extra 10 degrees warmer from what it was 10 days prior, or however you want to think of that. Okay, so in this case, the exact change in area is going to be the difference in the area above the x-axis and below the x-axis. Above means positive, below means negative. One thing I want to mention is that your graphing calculator can be used to find this. So I'll show you an example in our next video, but we're going to graph the function as y1. We adjust the window so the endpoints are visible. We use our second calc option. This is the same place we went to under calculators for min, the max, the zeros, things like that. We select 7 this time. You'll see what it looks like in just a minute. And then enter in the lower and upper limits, and it will show you the graph as well as the shaded region. So for now, we're going to just table that discussion until the next video so I can show you at the same time. Let's work through one example before I take a break. So we want to integrate this function 5 minus 2x with respect to x. And yes, it goes from 1 to 4, but we know about integration techniques. We learned about that in the last section. So the integral of 5 minus 2x is what? 5x minus 2x squared over 2. This time, I'm going to represent the fact that I have to substitute in the bounds from 1 to 4 with that long vertical line with the 1 and the 4 outside. I'm going to simplify this just a tad. So I get 5x minus x squared. And once again, I want to evaluate from 1 to 4. So what this means to do is it means to substitute the top number. Let's go down here with it. Put in the top number, which is 4, in place of the x. So we got 5 times 4 minus 4 squared. Then subtract the bottom number substituted in for x. So we've got 5 times 1 minus 1 squared. And calculate this answer. So 20 minus 16 is 4, and 5 minus 1 is 4, and 4 minus 4 equals 0. So all of that work, and the amount of area between the curve and the x-axis from 1 to 4 is 0 units. Now think about what a sketch of this graph might look like. It's just a straight line. It's 5 minus 2x. It's a linear function. Crosses the y-axis up here at 5. And then it goes down at a rate of 2 units down for every 1 unit across. That's the slope, 5 over, negative, what did I say? Down 2 over 1. So the slope is negative 2. Okay, so it does something like this, and it's going to hit the x-axis at 2.5, right? And then I'm finding the integral from 1 to 4. So here's 1 and 2, 4 is going to be right about here. And so from 1 to 4, the total area is what I've shaded in there. So it's 2 separate sections. This first section is above the x-axis. This section is below the x-axis. And so this would be a positive amount, and this would be a negative amount. And when you combine them together, you get 0. All right, let's actually go through one more example by hand, and then I'll show you on the calculator in the next video. So I want to integrate this function, 1 over e to the x minus 1 over e to the negative x with respect to x. We understand how to integrate. I might suggest rewriting this just a little bit first. How about e to the negative x minus e to the positive x if I write it without the fractions? It's usually something that people appreciate. And let's go this way with it, so I have room for a graph later. So I'm going to integrate e to the negative x. The integral of e to the negative x is e to the negative x over negative 1. I kind of messed up my x there. And then the e to the x integral is e to the x. And this, don't forget, we want to integrate from negative 1 to positive 1. So this would be negative e to the negative x minus e to the x. And it goes from negative 1 to 1. So you substitute the top number for the x's, and then you substitute the bottom number for the x's, and you subtract. And you end up getting 0, I believe. Let's see. This is negative, this is positive, that's negative, that's positive. Yeah, you get 0 for that. And so the sketch of the graph, which I'll do in the next video, would be shown such that part of the area is above the x-axis and part of it is below, and they cancel out to give you 0 for the total change.